with the topic next one, it is here waveguide dispersion. Next topic is now waveguide dispersion. Okay, the board is visible to all of you.
Yes, sir.
Okay, waveguide dispersion, including in that, in waveguide dispersion, already I have to know that what is dispersion. That is the optical pulse broadening in a single mode fiber. So waveguide dispersion is defined as a source of dispersion in a single mode fiber. Means in a single mode fiber, in any case of your pulse broadening is now happen, it should be known as your waveguide dispersion. It may be noticed that in single mode fiber only, it is almost in negligible multi-mode fiber. The waveguide dispersion occur because of some of the optical energy may be propagate in the cladding than the fiber core, and the fiber core and the cladding having different refractive index, so the light propagate at the different velocity in the core and the cladding. So at a result means that is your receiving of the optical pulse in the case of your waveguide dispersion is different from the enter to the optical fiber. So now waveguide dispersion is normally known as when the light enter to the core of the optical fiber, and when it to enter to the optical core, in that particular scenario some light get reflected go to the cladding part. Okay, so due to the go to the cladding part, cladding and core refractive index having different refractive index, so the velocity is also changing. So that particular velocity changing in that particular two scenario, at last the both of the waves having the reach at the different time at the output of the optical fiber. In that scenario, pulse broadening you should have received at the output of the optical fiber. So in that scenario, I have to write up the formula for the waveguide dispersion. There is delta TW. It should be equal to L by Vg. L is the length of the optical fiber. Okay, Vg is the group velocity. It should be directly formalized, that is your equal to Ln2 by C 1 plus delta d by dV into delta V. Sorry, BV. That is the formula of the broadening of the pulse. That is a waveguide dispersion is equal to L by Vg equal to Ln2 by C divide bracket 1 plus delta d BV divided by dV. Okay, it should be now delta should be now relative refractive index. It should be approximate equal to delta is equal to n1 minus n2 divided by 2. Oh, sorry, n2. Okay, V is a normalized V parameter. Okay, and B is a normalized propagation constant. B is a normalized parameter constant. Normalized parameter constant. Okay, normalized parameter constant or propagation constant. Propagation constant in that particular scenario. Okay, so now delta TV, it should be equal to the delta TW, means it should be also right DL dW, that is a dWL into delta lambda. That is a formula for the waveguide dispersion also. Delta TW is equal to dWL by delta lambda. So dW is known as a waveguide dispersion waveguide dispersion parameter. So dw should be write down. It should be equal to here minus of n2 by lambda delta c lambda into v into d by dv square vv. Okay, so this dw I have to write in that, and the finalized formula is no, it should be equal to the directly formula. I have to write up that dw for the numerical purpose minus n2 0.08 plus 0.549 into 2.834 minus v whole square. Okay, so that is the final sum derivative equation, including that the sum topic of your differential waveguide dispersion. So that is a numerically formula relation between, it should be deciding that is your waveguide dispersion including in that. That is numerical based upon your waveguide dispersion. Okay. A single mode step index fiber has following specification. First one is now fiber core refractive index, that is the n1 0.45, n1 is equal to 0.40, so sorry 1.45 core refractive index, that is your n1. Okay, relative refractive index difference, relative refractive index, that is a 0.5%. Okay everyone, now the third one is now material dispersion. Material dispersion equal to 6 picosecond kilometer hyphen nanometer kilometer hyphen nanometer at wavelength 1550 nanometer. Find out the diameter of the fiber core. Find out the diameter of fiber core to make total dispersion of the fiber zero. To make total dispersion of fiber zero at specified wavelength. So that is a statement of the numerical, that is a single mode step index fiber has the following specification. First one, that is your fiber core refractive index is 1.45, and relative refractive index difference, that is a 0.5%. Material dispersion, that should be now material dispersion, if you calculate, equal to 6 picosecond in the case of your kilometer nanosecond meter at the wavelength of 1550 nanometer. So find out the diameter of the fiber core, that is that you have to find out 2a. 2a you have to find out, that is equal to d diameter of the fiber core. Okay, fiber core. In that particular scenario, to make the total dispersion of the fiber zero, mean in case you have to discussion about the fiber core total dispersion formula is here dm plus dw equal to 0. That is your material dispersion and the waveguide dispersion equal to the 0. That is your total dispersion, that is your d. Material dispersion plus waveguide dispersion, it should be equal to 0. So material dispersion is your given now, that is a 6 picosecond. Okay, so dw is now means 6 plus dw equal to 0, and dw is equal to minus 6. Clear to everyone? Now your relative refractive index difference is given, means delta is equal to n1 minus n2 divided by n2 is given, that is a 0.5%, means it should be equal to 0.005. Okay, so according to this one, n1 is given, is equal to 1.45, means 0.005 is equal to 1.45 minus n2 divided by n2, and the final n2 is now equal to here, that is a 1.44. So that is the calculation of your n2, that is a cladding refractive index by use of your n1 and relative refractive index difference. Clear to everyone up to this point? Anyone having the doubt up to this end? Then to clarity to me, according to you have to find out dw equal to minus 6. So I have to write the formula of the dw as per find out in the previous waveguide dispersion. It should be equal to here minus n2 delta by c lambda, okay, equal to 0.008 0.549 2.834 minus v whole square. That is your complete formula. Okay, so according to dw, d equal to here minus 6. Okay, because that is the formula of your dw. In that scenario, dw is value is now point minus 6. n2 is now given. What is the value of n2? This one 1.44. Delta is given. This is given minus 1.4427 into delta is 0.0005. C is now 3 into 10 raised to power 8 into lambda is now 1500 into 10 raised to power minus 9. Okay. Next step is now, this is a numerical factor, this is a numerical factor, this is numerical, this is a V. What is the formula of V? V equal to, according to that particular solution, you have to find the value of V. V should be equal to 2.08 something from that particular equation. After the mathematical equation, V is equal to calculation is now 2.08. Okay, V is now given. So according to the formula of the V it should be equal to here 2 pi a n1 by lambda 2 of delta. That is the formula of the V parameter one. Okay. So according to this, V is given 2.08. 2a is now find out, that is a diameter. N1 is given, delta is given, and lambda is given. So final answer is 2a from that particular equation is equal to 7.1 micrometer. That is a D according to this equation. 7.1 micrometer. That is a calculation of the diameter you have to find out when the total dispersion is now. Next is now polarization mode dispersion. Polarization mode dispersion. So now basically polarized mode dispersion, that is known as here PMD. Polarization mode dispersion is defined as the difference in the propagation times, that is pulse broadening between two orthogonally polarized component of the light pulse in a single mode fiber. Means difference in the propagation times between the two orthogonally polarized component of the light pulse in the single mode fiber, because according to the light wave when it propagating through, it has the orthogonally, it should be now E plane and the H plane. Electrical and magnetic field, it should be now two orthogonally parameter including in that, that is your one is now H E. So according to the light wave travel in the polarization mode of between these two orthogonally parameters, so it should be due to this region the dispersion is happening, should be known as here polarization mode dispersion. So as per the fundamental mode of the fiber has two orthogonally polarized component, when the input light pulse excites both of these components, then they travel with difference group velocity. Means when these two orthogonally component travel with different group velocity and both components do not arrive at the other end of the fiber having the length at the same time, and the difference in the propagation time give rise to the pulse broadening. This is known as your polarization mode dispersion. Means a light wave having the consider of the two orthogonally component, due to these orthogonally component there are the different group velocity and the both of the component having not reaching at the same time at the optical fiber length, so that dispersion should be happen is known as here polarization mode dispersion. So according to the polarization mode dispersion, one parameter is defined in that, that is here modal MODA Bayer fringes. Modal Bayer fringes. Modal Bayer fringes. Okay, modal Bayer fringes. So what is the definition of the modal Bayer fringes? That is represent the actual difference between the mode index of two orthogonally linearly polarized component in a single mode fiber, and it should be mathematically, it should be known as here delta n, that is nx minus ny. Okay, nx and ny represent the respective mode of refractive index of the polarized component in x and y direction. Means the dispersion happening due to the two refractive index of two orthogonally component nx and ny, the dispersion happening should be known as here modal Bayer fringes. So in that particular moment that I have to define one component in that is labeled with the component, it should be equal to the delta beta. So that is a corresponding change in the propagation constant. So there should be defined as delta beta 2 pi by lambda into delta n. So propagation constant, it should be known as here propagation constant. It should be equal to here 2 pi by lambda into delta n, that is your modal Bayer fringes. Okay. So after you calculation the value of the modal Bayer fringes according to the propagation constant, that is your delta n, it should be equal to of here lambda by 2 pi into delta beta, that is a propagation constant. Okay. So now according to this one definition is more derived, that should be known as here beat length. Defining the definition, that is here beat length. So what is the beat length? It is defined as the length of the fiber over which the phase difference between two orthogonally polarized modes become exactly equal to 2 pi radian. So beat length, it should be denoted by your LP equal to 2 pi by delta beta, and delta beta should be defined as here equal to 2 pi 2 pi lambda into delta n. 2 pi is cancel out, so lambda equal to nx minus ny, so that is the LP is equal to here beat length according to this formula. Beat length is equal to lambda divided by mode index of two orthogonally component. It should be defining in this way. So according to the this expression, I have to define here pulse broadening dispersion polarized mode parameter. It should be now delta TPD PMD equal to L by Vx minus L by Vy. Okay. So according to the TBMD, according to the dispersion parameter, it should be now delta TPMD dispersion parameter.
हेलो सर.
Hello.
सर उधर विजुअल नहीं है सर.
Wait. According to the parameter delta T PMD is equal to here L divided by Vx minus L divided by Vy, and delta T PMD formula in case of your dispersion parameter dPMD under root of L. So that is some formula related with the dispersion parameter and the refractive index in the case of your group velocity, that in the case of your modal Bayer fringes in this category. Part, okay, the numerical is based on your PMD, that is a polarization mode dispersion in that case. Okay. So I have write the statement that a beat length of 10 centimeter a beat length of 10 centimeter in a single mode fiber when light ray of wavelength when light ray of wavelength 100 nanometer, sorry, 1000 nanometer is propagating through it. Okay, propagated through it. Calculate the amount of model Bayer fringes. Calculate model Bayer fringes. Okay, model Bayer fringes calculation now. So now, according to the formula of the beat length, you have to calculate the model Bayer fringes. That is the formula of the model Bayer fringes is now delta n lambda by 2 pi is equal to your delta beta, that is the propagation constant. So beat length is now given lp equal to, beat length formula is lp is equal to 2 pi by delta beta. Okay, lp is given, 2 pi is given, you have to calculate the value of delta beta here, that is a 2 pi divided by your, okay, so that is the answer is now 2 pi 10 centimeter into, if you calculate the meter minus, that is the answer is now delta beta 2 pi by 10 raised to power minus 1. Okay, so now according to the model birefringence, lambda is given, that is 100 nanometer, 1000, that is 1000 into 10 raised to power minus 9, 2 pi, delta beta is 2 pi by 10 raised to power minus 2 pi cancel, that is 10 raised to power 3 minus 9 plus 1, that is a 4, 10 raised to power 6 is now delta n, that is a model birefringence according to the formula, that is a 10 raised to power, sorry, minus 9, that is a minus 6 is now answer, that is equal to here 10, sorry, 10 raised to power minus 6 is now answer. Calculation by according to this way, if you calculation, okay, so that is a calculation of the model birefringence, or it should be write up equal to here 10 micrometer 10 ratio minus 6. Okay, so that is the calculation of the beat length by the using of the model birefringence one. Check out this numerical, that is clear to all of you. Now start with the next numerical, an average PMD parameter, an average PMD parameter, that is your DPMD, equal to 10 picosecond under root of your kilometer. Okay, is specified for a typical single mode fiber. Specified for a single mode optical fiber. Okay, if the fiber length is, if the fiber length is 100 kilometer. Find PMD, that is a pulse mode dispersion, polarized mode dispersion, induced pulse broadening. Induced pulse broadening. Statement is now an average pulse mode diameter, pulse polarization mode diameter parameter is 10 picosecond under root of kilometer is specified for a typical single mode fiber if the fiber length is 100 kilometer and the PMD, find out PMD induced pulse broadening, means you have to calculate the value of TPMD, delta TPMD. According to the formula, that answer is TPMD, PMD under root of L. D value is now 10. Fiber length is now 100. So this is the formula, and finalized answer is now 100 picosecond. So that is the only simple formula. There is the pulse polarization mode dispersion according to this one. This is the delta TPMD according to this formula. That is deal with the numerical of here mode field diameter. Okay, mode field diameter. That is some concept is now. I have to write up directly formula for the numerical. The core diameter of a step index fiber. The core diameter of step index fiber. Core diameter of a step index fiber is 8 micrometer. The value of core refractive index and relative refractive index, that is your core refractive index is now n1 is equal to 1.46 and delta is equal to 0.3%. Okay, the core diameter of a step index fiber is now 2a, that is at 8 micrometer, n1 is 1.46 and the 0.3% is now relative refractive index difference. So calculate mode field diameter MFD at wavelength of 1550 nanometer. So according to the formula of the mode field diameter, MFD mode, that is your mode field diameter equal to, that is the 2a 0.065 plus 1.619 divided by under root of V3 plus 2.879 divided by under root of, sorry, not under root here, only V6. So that is a formula of mode field diameter. According to formula of the V is equal to 2 pi a by lambda n1 by 2 lambda delta. That is the formula of the V parameter. So according to this one, mode field diameter you have to calculate. 2a is now given 8 millimeter. V is now calculate 2 pi a. Okay. Diameter is given 2 pi a, n1 is now given, delta is now given So after the put up the all the value of the V here, the value is now 1.834. That is the value of V. V is put up the value according to this equation. That is a V under root of 1.834 cube plus 1.834 whole square of the sixth one. So finalized answer is now 11.0196. The answer is now 11.0196 mode field diameter. That is in case of your micrometer. That is a numerical based on your mode field diameter one. So now this is your numerical part as per the discussion with the dispersion parameters.